This is MAGR 2156, Sophomore Design Engineering Lab. My name is Justin Dalton. I'm the lab manager down here. I'm going to be walking you guys through the very beginning stuff that we have to go through in preparation for the course. During this lab, before you come in, you need to make sure that you have your own personal safety glasses prior to coming into the lab. Do not ever enter the machine shop without wearing eye protection. We will talk more about that in a moment. I would suggest that you take some notes and review the content of what I'm going to talk about today. Even though you can reference the video, it's helpful to take some notes. Some of the safety items that we're going to go through in the very beginning, I will outline them, and it's important that you pay attention to these because they can prevent you from being injured in the shop environment. One of the first things that we're going to talk about is shop appropriate clothing. Mainly, what we're concerned with are things that can be caught in a piece of rotating equipment. Items such as long sleeves, hoodies, ties, any type of baggy clothing, any type of cloth that could get caught or snagged in a piece of rotating equipment are prohibited from being worn down in the shop while operating equipment. We do not allow gloves to be worn in the shop. This is a safety concern. A glove can get caught in a piece of equipment, it can get caught in a spindle, it can be pulled down in, and you will not be able to get that glove off before your hand gets pulled into the equipment. If you have long hair, it needs to be tied back safely and securely. It needs to be down your back. It can't be draped over your shoulder. Closed-toed shoes are required in the shop at all times, whether you're working on the equipment or not. So please don't come into the shop without closed-toed shoes on. We don't allow any jewelry of any kind that can be caught in a piece of equipment, such as bracelets, rings, watches, necklaces that hang outside of the shirt. Everything that is a jewelry item must be tucked inside of your shirt, and no jewelry items are allowed to be on the wrist or hands. Please don't bring your book bags and coats and stuff into the shop. There are lockers provided. Put those items in the lockers, please. You're going to be required to keep a lab notebook. Your course instructor will talk to you about the requirements of a lab notebook whenever you show up to class. You will have to bring a release form to class prior to being allowed to work in the machine shop. We will have to have those release forms signed, and you will not be allowed to work in the shop without a release form on file. They will be provided for you either in an email or on the website. Safety glasses. I addressed this at the very beginning, but it is a major concern. Please do not enter the machine shop area without wearing safety glasses. This needs to become a habit that is second nature for you. Don't take your safety glasses off while you're in the shop, and please make sure that you have them over your eyes prior to walking through the doors of the shop. This is to prevent flying metal from going into your eyes. It's to protect you and your vision. You will need to purchase a toolkit for this lab. We will provide the information on how to obtain a toolkit in the introductory emails and on the website. You need to print off a full set of prints and bring them with you every single day that you come to class to work in the machine shop. This does not only apply for the sophomore engineering lab, but also any time subsequently thereafter that you ever work in the shop. You are required to have prints to work in the shop. You're not going to be working off of memory or creating as we go. That's not what we do down here. Phones are not substitutions for a print during the sophomore design lab. You must have either a paper print or a paper-sized electronic print. Please don't use your phones during the demo. Obviously, that's more of an in-person item, but anytime the instructor is talking, please do not have your phones on. Please respect other people's tools. Don't go into somebody else's toolbox just to borrow something. It sounds kind of silly, but it does need to be said. Please make sure that you are only grabbing your toolbox whenever you leave. I would suggest identifying your toolbox, personalizing it somehow, and making sure that you can look at your toolbox and know instantly that it's your toolbox so that you don't accidentally grab someone else's tools. SDS sheets, formerly known as MSDS sheets, are available for any of the materials that we use in the machine shop. Safety data sheets are an explanation of the health hazards and the reactivity of any of the different chemicals and things that we would use that you may come in contact with in the shop. Those are available on any of our computers. They can be made available to you at any time that you would like. The two items that you will come in contact with in our shop are low reactivity, low health hazard items. There is a cutting oil and a lubrication oil that we use regularly in the shop, and those are likely to be the only two items that you ever come in contact with. One of the things that we will stress during this course is that we maintain a clean shop environment. You are responsible for cleaning up any and all mess that you make. If oil gets sprayed all over the walls during your machining activities, you're required to clean the walls. If you throw chips, metal chips and shavings 20 feet in diameter, you're required to clean that 20-foot diameter. So please be mindful of any messes that you're making. Some of it is unavoidable. You are just required to clean that area. You are required to clean the piece of equipment that you are using after you're finished. And you're also required to clean the floor area around the piece of equipment that you're using. So please allot time to make these cleaning efforts. Grading and attendance policies are going to be covered in person or on the introductory emails or on Banner or the other websites that are available to you. This is the air engine that we will be making. This project covers the vast majority of all of the basic machine shop operations that you will likely need to make most parts down in the shop. Now obviously these are just the basic operations, but this is a very good place to start and you end up with a pretty nice project. In our machine shop, we use English measurements or inches for all of our measurements because that is what our equipment is set up in, is in inches. Whenever you're using an English scale, the divisions are going to be in inch units. A scale is what some people would call a ruler, but the difference is on every scale you have different divisions where the little tick marks on there represent different amounts or measurements. This, for instance, is a 16th scale on this line right here, which means that every tick mark that's on here represents 1/16 of an inch. So if we counted 1, 2, 3, 4, that is 4/16 of an inch, which simplifies to 1/4 of an inch. If you have any questions about reading a scale or English measurements, if you're not familiar with that, please ask your instructor. As engineers, we are going to constantly come in contact and need to use many different types of materials. One of the things that we like to do to help ourselves decide which materials to use many times is to start to break things down into categories or classifications or groups. One of the major subset of groups that we typically will classify materials into as engineers are ferrous materials and non-ferrous materials. Ferrous materials meaning that those materials have iron as their main core constituent, and non-ferrous materials meaning that any iron that's in them is usually a trace amount. There's a very easy way, it's not foolproof, but there's a very easy way to tell if something is ferrous or non-ferrous. We use a magnet. If it's a ferrous material, the magnet will stick to it. If it's a non-ferrous material, the magnet won't stick to it. If we're not sure, it gives us an idea of what the material might be. One of the things that you will notice about the different materials is that they have a different look. So what I'm going to do is talk about non-ferrous materials first, and then we'll talk about the ferrous materials. Non-ferrous materials include items such as copper, brass, and bronze. One of the most prevalent is aluminum, and you have many other items such as titanium and zinc and many other engineering alloys that you will come across. One of the easiest ways to start to delineate between the two materials, or the two subsets of materials, is color or look. One of the things that you'll notice about copper is that it has this reddish rose type color to it. Brasses and bronzes look gold. Aluminum is a whitish silver color, or a gray type of color. Now, that's not definitive. You can't always go by look, but it is definitely one of the things that we will go by to start trying to figure out what something is if it's not marked. Non-ferrous materials also include items such as plastics, wood, ceramics, things like that. So there's a huge subset of materials that we will use in engineering that are non-ferrous materials. A lot of times what you will run into with the non-ferrous materials are that they tend to be soft or softer, relatively speaking, when compared to the ferrous materials. It's not always the case. Tungsten, for instance, is extremely hard. There's no iron in tungsten. So it's not an all or nothing. We use aluminum a lot as an engineering material. Most people will tell you the reason is because it's strong and lightweight. While there is some truth to that, the reality is that a component that's properly designed out of aluminum and out of steel, they should weigh about the same, because aluminum and steel have roughly the same strength to weight ratio. So that too is not always the case. One thing is true about aluminum: it is much, much softer than steels are. We exploit that, and we'll talk about that more here in a little bit. Copper, again, very soft material. We use that to our advantage. So those are some of the non-ferrous materials. Now, some of the ferrous materials. Steels. We all know that steels are the backbone of many engineering projects. They are very, very strong. They can be made into many different shapes. They can be forged. They can be melted and poured in casts. They can be machined. And for those reasons, we use a lot of steel in engineering projects. These are some examples of steels that you will see during your lab and around the shop. They're just different shapes, and there are also some different alloys. These bars are just some low carbon steels. Now, you'll learn more about carbon content and its relationship with steel in your materials class, but in general, the lower the carbon content in the steel, the softer it is, and the less readily it will accept a heat treat. Now, there is a line of carbon content that will not heat treat, and I'm not going to go into heat treatment very much, but you just need to know that. When we refer to something as a low carbon steel, it basically means that you can't heat treat it readily without adding more carbon to it at some point. This material right here is a low carbon steel, and it's a low carbon square stock steel that we'll be using to make the air engine components. This is a round bar stock low carbon steel that we'll be using. Now, these rods are a different type of steel. They're a different material. This material is called drill rod, and drill rod is made from a high carbon steel. It is an annealed tool steel. So annealing is a process where you heat treat the material in order to soften the material so that it can be readily worked or machined. One of the things that you'll notice about drill rod is that it has also been processed after it was through the mill process. These materials here, you can see, are kind of dull. They have some patchiness to them. The finish is not exquisite, whereas these pieces are very uniform. You'll notice that the finish on them is very regular. You don't have any real difference in the finish from one end to the other. These also are a very brilliant silver type of finish, all indicating that it has been processed after the fact to achieve a certain goal. Drill rod is very round, and it also has a close dimensional tolerance, meaning that if I say this is 1/4 of an inch or 1/4 of an inch, it will be 0.250 inches. We'll get into tolerancing and how big and how small a thousandth of an inch is later on, but it's a pretty tight tolerance on this material. Now, tool steels are a type of high carbon steel. And like we said, high carbon steels, the difference with them is that they can be readily heat treated. So we now have to know what the heat treatment state is on the material when we go into high carbon steels. You can get high carbon steels that have already been heat treated, or you can get high carbon steels that have an annealing process done to them so that they're softer and more ready to work. One thing I will point out is this piece of material has an obvious defect in it where someone bent it at some point in time. You want to avoid these areas around this because this right here is not what we're looking for. When we choose a material that has a very regular dimensional shape, we want that regular dimensional shape and not some bent version. This tool is called a vise, and if you notice, you'll see the difference in color between the vise jaws and the body of the vise itself. We've got our magnet here. You can see that the magnet sticks to the body of the jaw, but it doesn't stick to the jaws. Now, the reason for that is that the jaws, we would like for them to be softer than what we are clamping on. In this case, we're going to clamp on this piece of drill rod here. If we had a hard jaw in there and we clamped onto the part, what would happen is that the part would likely be damaged. We don't want that. We want to preserve the part, so we have these jaws that are softer in there as semi-sacrificial, so that if any damage is taken, it goes into the jaw versus the part itself. Now, the reason we're putting this in the vise is so that we can hold on to it so that we can start to cut it. But prior to cutting it, we have to know a couple of things. We have to know, can we cut this material with a saw? How do we figure that out? One of the ways that we can figure it out is using this tool right here, which is a file. And a file is a hand tool that is one of the more rudimentary tools that we use, and it just allows us to cut burrs or sharp edges off of the parts. And as you can see, we've got a corner right there. If we push you can see that it is starting to cut the edge down. Now, it's a slow process. It's not meant to be a fast process. But what this tells us is that this material can be cut, this material here can be cut with the file. So if we have a question about a piece of material that we don't know whether or not we can cut it safely in the shop, one of the first things that we're going to do and we're going to ask is, have you tried to cut it with a file? If you bring it over to a vise or something like that and you take a couple of strikes with the file and it cuts it readily, the likelihood is very high that we'll be able to cut it with most of the tools that we have available in the shop. If not, we're going to have to explore some other methods. Doesn't mean that it can't be cut, it just means that with standard traditional tools that are available, you're probably not going to have very much luck with it. The reason for that is the rule of law in the shop, that is, what you are cutting must be softer than what you are cutting with. It sounds kind of silly to even have to say it, but you have to be that way. You have to have a harder tool and a softer material that you're cutting. That's part of the reason that we talked about the annealing process just a moment ago. This material has been annealed. It means that it's been softened up so that this material here which has been hardened with a heat treat process, can cut it. Now, these two materials are chemically almost exactly the same. The difference is the heat treat between them. I go through an example whenever I do my in-class lectures of butter. If I want to cut a stick of butter, I will go to the drawer and get a butter knife. I can take the butter out of the refrigerator and I can use that knife. Cuts right through the butter. How do I know that? Well, there's a lot of reasons why. I've done it my entire life. I saw somebody do it. Now, if I go to the refrigerator and get 2 sticks of butter and I use a stick of butter to try and cut another stick of butter, the likelihood is that I'm just going to make a big mess. The same thing happens here. If I got a piece of material like this and I tried to cut a material that's the same, I'm just going to end up with a big mess. Now, I told you that these two materials are essentially the same, and the difference is the heat treat. How could I bring that in to the butter example? Well, we know that the knife that I cut the butter with is much, much harder than the butter. And it's also a different material. That would be an example like taking a saw blade and cutting through a piece of wood, for example. But these two materials are the same, so what's an example like that? Well, essentially it would be the same as if I took a piece of butter and I formed it into a knife and I put that knife made of butter into the freezer and then took another piece of butter and set it out on the counter. So essentially I'm annealing the butter that's out on the counter and I'm hardening the butter that's in the freezer, and I could take that knife made of butter out of the freezer and I could cut right through the butter that was on the counter. That's essentially what we have going on here. So, what I'm going to do is I'm going to lay out my part, which means that I'm going to basically put a tick mark on my part with a Sharpie or some sort of marker. I've got it securely fastened into the vise. I've already checked to make sure that this material can be cut with the file. And now we're going to use one of the very first hand tools that you're going to see, which is a hacksaw. Now, many of you will probably be familiar with the hacksaw. You've probably used one at home. It's no different. And just like the file, the hacksaw only cuts when you're pushing away from you. As you saw in my demonstration earlier, I was pushing the file, and that's not by accident. A file cuts when you push it away from you. A hacksaw, when the blade has been mounted properly, will cut when you push away from you. One of the things that you will notice is that if I were to just drag this saw back and forth on this round piece of material, it's going to tend to walk back and forth, and that's not what we want. So what I do is I use my other hand and the vise to steady the saw, and I will make some short strokes to generate a little groove. You can see the small groove there, and that small groove, once it's established, will help to keep the blade from walking back and forth, because it's going to want to stay in that groove. Once you get that little groove, we can then make our strokes a little bit longer with the saw, and we can cut the rest of the way through the material. So we've cut the blank for our very first part. Now, one of the things that you will notice, it's going to be hard to see on the video, but I'm going to try and take some pictures of it to show you guys examples of burrs. It's the little sharp edges that are formed whenever you cut. We need to get rid of those because burrs are problematic for us at many different levels in the machine shop. One of the ways that we can get rid of burrs is with a file. Now, if I have the piece held in a vise, I can go around the edge with a file. It's a little bit awkward on these small round parts. If you're holding it in your hand, you can see it's a little awkward to do this with small round parts. However, if I have a rectangular piece, something like this part right here, and I want to take a burr off that edge, a file is my go-to because it works extremely well and it's very fast. Just like that. So what are my other options? Well, that leads us into the first piece of power equipment that we're going to talk about, the belt sander. This is a power sander or a belt sander. The belt, as you can see right here, it will be spinning when the motor is engaged. It moves downward like that and pushes against a work surface. If you can, you always would like to have your workpiece against the work surface. That will help to secure it and make it a safer operation. It's not always available. You can't always do it, but that's the ideal case. This is a cover. This work surface right here, if you need to adjust it, the angle is adjustable. There is a pusher that you can use. We normally store this separately from it because a lot of people don't need it very often, but it is handy to have from time to time, and you can see it has an angle adjustment available on it as well if you want to do some things repeatedly. The front buttons on the cover here allow you to turn the sander on and off. The green button obviously turns it on and starts it. The red button stops it. It does get a little loud when you start it up. Don't let that alarm you. Here you go. As you can see, the belt doesn't stop immediately, so please make sure that you are aware of how long the belt is moving before you move away and clear away from the machine. If you have a part such as the piece we just cut, you can lay that part, if it's long enough, down on the supporting work surface, push it against the belt like that while the belt is running, and you can rotate it just like that. All of that while the belt is running, obviously, just like this. Now, if you notice, I didn't try to make the end flat or square or anything like that. All I did was cut those burrs off. All we're doing is getting rid of those sharp edges on this operation. If you noticed also, I held it at an angle. That way I'm not pushing this thing straight into the belt. There's a couple of reasons I don't want to do that. One, if I do that, it's going to create a new burr straight down. So what we actually want to do is hold it at an angle and turn it so that we trim the edge off all the way around. We don't need to put a big chamfer on it. All we need to do is just break that edge off so that whenever we run our fingers across that edge, we don't feel any sharp edge anymore. We don't want anything hanging over the edge. What do we do if we have a part like this that we just cut off? This part's not very long. What we have to do at that point is we actually have to hold the part and bring it up to the belt. I can't set that part down like that and control it. I almost literally cannot pick it up off of that work surface. So that definitely means I'm not going to have control over it, which means that it's not very safe. You don't want this gap back here to be larger than 1/8 of an inch, because then you can get parts that will suck down in behind there and they'll get either stuck, or if you had a long part, it could potentially pull you in. It's another reason we don't allow gloves in here. What you need to do is hold the part at some level angled down, because when it's angled down, the belt can't catch it. It can only kick it out a little bit like that. If you're angling it up like this, it could wedge in there and catch and drive the part down either into your hand, or flip it out of your hand, or pull it down in between the table and the belt. All of those things are not good. So if you're going to use this like this, what I do is I rest my hand away from the belt and I bring the part in, and I will slowly rotate it, and I may stop and reorient the part so that I don't have to get close to the belt. Just like that. Take the burrs right off. This is a section of saw blade off of one of the power saws that we'll talk about in a moment. This is just a piece of aluminum. What I'm going to talk about is the number of teeth inside the cut at any given time. This is a relatively coarse blade. This is the blade that is mounted on our horizontal bandsaw. If you look, there are times when there is only one tooth in the cut. That's not ideal. We need a minimum of 2 teeth in the cut at any given point to prevent the teeth from grabbing on the material. If you think about the material here and the teeth here, if your material is very thin like this and your teeth are very coarse or spaced far apart, they can grab onto the material and pull it. So we need to make sure that there are enough teeth in the material at any given time to support the cut. So if we were cutting the material where the blade passed through it this way, such as going through like that, then this would be okay. But if we're cutting through it like that, then this would not be okay, because there's only one tooth in the cut at certain times, and that's not what we want. Blade pitch is given in the number of teeth per inch. So an 8-pitch blade means that the teeth are 1/8 of an inch apart. This blade is an 8-pitch blade. You can see there are 2 teeth right there at the extremities. This is a 1/4 inch piece of material. So we don't want to use this blade to cut this material in this orientation. Likewise, we don't want to use a blade that is too fine. The hacksaw that we had earlier, this has very fine teeth on it. It may be even difficult for the video to pick up. This has 24 teeth per inch. And this piece right here is a little over 1.5 inches, which means that we would have almost 40 teeth in this cut at any given point. That's too many. We have to find a balance of where we want to be. If we have too many teeth, as the teeth drag through the material, the blade fills up or loads up. The teeth become clogged full of material, and there's nowhere for the material to go, and subsequently they just drag. They usually end up creating a lot of heat, and the blade fills up, everything starts to heat up, it doesn't cut, you run into problems. Something like this would be ideal, where you've got a lot of room in the teeth for the material to cut, because the material goes into this little swoop. That little swoop is called a gullet, and that's where the chip goes. Whenever the tooth is dragging through the material like this, that chip is formed and it goes up into that little swirly area. So it's important to remember a couple of things. Whenever we're going to one of the power saws, it's important that we make sure that we don't have too many teeth in the cut at any given point in time. A good rule of thumb is you really don't want to get more than about 20 or 30 teeth in the cut ever, because it's just too much. You don't want to have too few teeth in the cut. We need to have at minimum 2 teeth in the cut at all times, preferably 3 teeth in the cut at any given point in time. So if you'll keep those things in mind, we can talk about the saw. This is the power control setup for the vertical bandsaw. There is a lockout lock on the side that you may or may not encounter whenever you go to use the saw. If it needs to be removed, you can remove it. And this switch allows us to turn the power on to the machine. When the switch on the vertical machine is in the vertical position, there is a little insert inside of here that allows you to see it says on. And whenever you turn it over here, there's a little insert in there that says off. These buttons right here control the power to the blade. The green button turns the power to the blade on. The red button stops the power to the blade. If I turn the main power switch on and I hit the green button, you can hear the saw fire up. And if I hit the red button, you can hear the saw cut off. Now you can also hear the saw coasting down, which is something that we have to be aware of. That blade is still moving after the power to the machine has been cut off. If we are going to go into the saw, which we will be here in a moment, I'm going to cut the main power switch off, and I'm going to see if I can turn the machine on by pressing the green button. This is just a safety check for me to make sure that I don't have power going into the machine. Another good option is to ensure that the lock is in the lockout, because now I physically cannot turn the power onto the machine. In this orientation, you can see the teeth of the saw blade have a downward angle. These teeth are facing down in this orientation. The downward facing teeth should push the material down onto the work surface. When the blade is on, the band will start to spin. Now I have the power turned off to the machine and I've checked it. I've checked my power. I can open the door, turn this handle and open the door. And we can see the band turns around. Now below, I can open this door. And we can see, you can leave it down. Whenever I turn the top, the bottom drives around. This is a guard, and this is a guard. They just protect you from the moving blade. This guard is easily removable by simply lifting up on it and taking the guard off of these two socket head cap screws. To replace it, I simply hook it back over and hang it there just like that. I'm going to remove this guard so that you can see the inner workings of the saw. This blade right here will be moving like this. The blade moves down and it pushes the chips down through. We'll have a piece of material resting on this work table so that you can cut the material, and we will push the material through the blade. We need to keep in mind the number of teeth that are in the cut at any given time. I've already verified that for this thickness of material, and it's okay. We always want to make sure that the guards are in place prior to doing any metal cutting. One of the things that we want to do is we want to make sure that we don't have any more blade exposed than we need to have exposed, meaning that there is a set of blade guides just like this right here, and there's a set that are right below the table. We want those guides as close together as we can have them in order for the blade not to try and walk around on you. We can move the blade guides up and down by adjusting this handle. We'll want to place our hand beneath the blade guide holder and loosen this, and that will allow us to raise and lower the blade guide assembly. If we have it like this, and we're cutting something thin like this, we'll have this much extra exposed blade, which can pose a hazard for getting cut if you bump into it. What we do is I'll normally put the material under this. I'll loosen this and lower it down. And now my material will slide under there, and the blade guides are very close together. If we decide that we need to have a different blade on the saw, we can change the blade. Maybe the blade is dull, maybe the blade has teeth missing, maybe the blade is either too fine or too coarse and we need to change the blade. The way that we do that is by the following steps. This handle right here is the blade tension handle. We can adjust this handle by turning it, and as we turn it, you'll notice the blade tension indicator moves up and shows the tension relaxed. We'll continue to turn it, and as we turn it, you'll start to see some slack form in the blade. There's the slack coming into the blade. This is letting us know that the tension has been removed from the blade. We will carefully pull the blade off, and that blade has now been removed. We'll go through folding a blade in a moment. Once you have the blade that you want to put back on the machine, the first thing you're going to want to do is start with the blade higher than you think you need it. And we're going to hook the blade over the top of the top wheel. That gives us a place that we can hang the blade safely and work on where to position the blade. The next thing we're going to need to do is route the blade behind the blade guide on this side. We need the blade to go behind that blade guide, and if you notice, I've put my free hand up on the top wheel to keep the blade from jumping off of the wheel. I move to the other side. I'm going to hold the blade onto the wheel for the same reason, to keep it from jumping off. And I need to put this blade into the guides. The most important guide to focus on is the one beneath the table. I'm going to reach under here and put the blade in that bottom guide. If you notice, when I did that, the top guide, the blade went right into it automatically. We're going to now focus on the underside of the machine. On the bottom side of the machine, what we're going to do is make sure that the blade is on the wheel and double check that it is behind this guard. Once I've done that, I've checked the bottom to make sure that the blade is roughly centered. I've checked on the top to make sure that the blade is roughly centered on the wheel up here. Now, we can start to add tension to the blade, and you'll see that the slack is starting to come out of the blade, and it will start to tension it. You start to see that there's some tension forming. And we're going to turn this handle until the blade tension indicator reaches the bottom of this little groove that it's in. You'll see it moving down toward the bottom, and once it touches, there's enough tension in the blade. I'm going to replace the guard. And I'm going to close the doors, making sure to turn the door locks. And the blade has been changed from one blade to another. The next thing that I'm going to do is turn the power back onto the machine. Turn the power back on, hit the green start button, let it run for a second, and I'll turn it back off. I'm going to stand here with the machine until the blade stops coasting. Alright, the blade has stopped moving. Now I can move away from the machine and we'll be ready to make a cut. Things that we need to consider when using the saw are, will my material move whenever I'm cutting it? This is a piece of round stock. If I were to push this material into the saw blade, it's going to spin. So we need to control that movement. We have a vise right here that we leave at the machine in order for us to hold on to that. We can grab the material in the vise, and if you'll notice, this vise we've turned upside down. We put the vise upside down, it holds on to the material, and we can then use it to prevent the material from spinning around in a circle. If we wanted to cut a thin piece of material, I'm using a sheet of paper as an example. We may have a piece of sheet metal or something that we want to cut. As the material is pushed in, you'll notice that it's pulling that material down. And you can imagine if we were trying to run the saw and cut this, it would fold the material down into the saw. And that's not what we want to have happen. So what we need to do is we'll create a work surface that is closer to the blade. And we do that with a piece of scrap material, such as a piece of plywood. We can turn the saw on. And we now have an artificial work surface. We now have an artificial work surface that will prevent the material from being pulled down into the machine. This is also a handy method whenever you're cutting off very small parts that might get lost down in the machine that you may want to have cut off in the saw. One thing you may want to use is a pusher block. And a pusher block is nothing special. It is really just a piece of scrap wood that we can use to help us push if things get close, to keep our fingers out of the way. Ultimately, that is our goal. Keep your fingers away from the blade. Make sure that we can operate the machine safely. I tell people, when you look at this machine, you'll see this line here. We use it to feed the blade up into the machine, but it's a good visual representation of what you should never cross with your hand, wrist, arm, anything. I always want to keep one hand on one side and one hand on the other, or both hands on one side, such as this right here. What you don't want to do is something like this, or something like this, because you could be cut by the saw, and those injuries are very, very, very painful. I'm going to cut this piece of material off. I'm going to use a pusher block behind it, like that, to support the cut. I'm going to turn the saw on. I've made a mark on my piece of material where I'd like to cut. My hand was completely clear of the machine in the entire time it was making the cut. The pusher block helped to support the cut so that I didn't have to push with my fingers anywhere near the blade. Now, I held on to this side of the material because my part was long enough for me to do so. If my part did not allow me to do that, if I was cutting off a little thin piece on the side or whatever, and I was left with a part sitting up at the blade, I can use a pusher block to clear my part away. You never want to use your finger to flick a part out of the way anywhere near a running saw. Once you take the blade off of the saw, you're left with this big blade and there's nothing really simple to do with it. So what we do is we fold the blade up. One of the easiest methods that I have found to fold the blade is to set the bottom of the blade on the ground and put one foot in the saddle of the blade. Take your hand and reach around the top of the blade with your knuckles facing your chest and grab onto the blade like this. It's a little bit awkward feeling at first, but grab it like that. Again, I'm going to reach around where my knuckles are in my chest and grab onto the blade. I'm going to gently rotate my hand back to its normal position as I bend over slowly, and you can collect these loops at the bottom. I make this look very easy. It takes practice to do it, but it is not something that is very difficult. If you have loops that are different sizes, you can just bounce it in your hand and it'll fix the problem. Now, whenever you go to put one of these folded blades on the machine, what we're going to do is unfold it carefully. Don't ever unfold it towards someone. have it unfolded, and then we need to look at the teeth. The teeth are on the side of the saw facing us. So the flat side of the blade is toward the back of the saw. The teeth are toward the front of the saw. The other thing that is very important is that the teeth of the blade face downward. I'll show you an example of a short piece of saw blade where the teeth are facing down. This is an example of the teeth facing down. And then you load the blade back onto the saw. These are the controls for the horizontal saw. Horizontal saw has a blade that runs horizontally. The controls are broken up into two sections. This section controls the band going around in a circle, or the band power. If I hit the green button, the band will start spinning. If I hit the red button, the band will stop spinning. This saw is a semi-automatic saw, meaning that we can lift the head of the saw up and control how it cruises down. That's what makes it semi-automatic. We can fix how fast or slow the head moves down. And we do that with these two controls. I tell people to think of these two controls like the controls in your car. This control down here, which is the feed hold switch, works like a brake on your car. If you want the head to stop coming down and you want it to stop, you turn this to the hold position. If you want it to be able to move down, you turn it to the feed position. So it's in the hold position right now. This right here is more akin to your gas pedal. If we turn this knob clockwise, gently, we don't want to ever turn it hard. If it stops, you want to stop turning it right there. If we turn it clockwise until it stops moving, that is the minimum feed that is allowed. If you turn it counterclockwise, one full turn, you should have seen a mark on the front there, turn one full revolution, that's where you want it to be for pretty much anything you're ever going to cut in this shop. In order to feed, we would turn this knob down and the head will start to come down slowly. When I walk up to the saw, I'm going to first turn the feed hold on and lift the head. You physically just lift the head of the machine up like that, and the feed hold will prevent the head from coming down. In order to feed the head down, I can release the feed hold over here, and you'll see that the head starts to come down. Now, I have turned the feed up dramatically so that you can see the head come down. Normally, what that will look like is this. It's very slow. That's what we want. If I want to start the band, I can hit the green button. Now, when I hit the green button, you're going to see two or three things happen. You're going to see the band move. You're going to hear the motor turn on. And the other thing that you should see is some coolant come out from this general area where this tan bar is. So I'm going to hit the green button. That lets me know that whoever used this last did not have the guide tightened. That needs to be tightened. It's an adjustable guide. There we go. I should start to see some coolant flow. And if I don't, I can check this valve right here. And if I turn it on and it still doesn't flow, then I need to contact one of the shop supervisors or one of the TAs for them to come figure out the problem. We know what the problem is with this one already. We don't have any coolant in this saw right now. That's okay. So, whenever I set up cut something, I need to make sure that all of the things that we talk about with the other saw are in place. We want the blade guide to be as close to the material as possible. So I can loosen this, close it down, tighten it up. That's closed as it gets. I'm going to turn the feed hold on. I'm going to lift the head up, and then I can show you how you can clamp materials. Normally you don't need to lift the head up anywhere near that far, but I want you to be able to see the vise mechanism. This is a coarse adjustment for the vise. It allows us to open and close it very quickly. You'll likely want it to be in the very first groove. If I put a piece of material in, and it's as long as the vise is, I can turn this handle, clamp on it, and once I tighten this clamp handle right here, that material will be securely held, and I can start the sawing process. I'm going to bring the head down close to the material. Slow this down to the desired position, all the way closed. One turn counterclockwise. Now we can cut this off. So once we're prepared to make a cut, we have selected our material. We have made sure that the number of teeth are adequate to cut this material. We have put our blade guide as close as we can for the material we're cutting. We have verified that once we start the saw that we have coolant flowing. So all that's left to do is to position the cut. What I like to do on this particular saw is to position the length of cut that I want with my right angle framing square that's in your toolbox. And I will use this edge to push the material, and I'll use this edge of the scale to stop on the blade itself. What you're left with is the amount of material that you want sticking out of the saw. There again, I will use this to push the material and this to stop on the blade. Now, in order for that to work, obviously your blade must be relatively close to your workpiece, but you definitely don't want the blade to ever be touching the workpiece whenever you're trying to move it around and set your length. Once I'm happy with where the piece is going to be cut, I will tighten up my vise and do a double check to make sure that the length hanging outside of the blade is what I want to cut. Now I'm ready to start the cut. I want to turn the speed to where I want to cut at. I'll turn the band on, look for the coolant to flow, and then I can release the hold. A good thing to always do is double check that you are clamped. I am. Start it, look for the coolant. I've set my speed. And let the saw do the work for you. Once the saw reaches the bottom of the cut, it will stop automatically. It will turn itself off. Do not try to retrieve the part until the blade has stopped moving. Once the blade has completely stopped, you can then retrieve your part.